Sections 4.1, complex numbers. I am learning to identify, graph, reduce complex numbers. Our very first vocabulary word is imaginary units. Imaginary unit is the variable I. And we can say I equals the square root of -1. And the opposite of a square root is a square, so if we square both of them, we get I squared equals a -1. So those are all of the parts of our imaginary units that we have to have. Our next vocabulary word is complex numbers. And complex number is A plus BI, in which A is your real and BI is our imaginary units. Ooh. So complex numbers on a coordinate plane. So that's our next part we're going to look at. So we're going to see how we're going to graph that A plus BI. So complex numbers on a coordinate plane. So basically, how to graph. So in order to graph them, we write them out like an order pair as A, comma, B. So if you think about it, A comes first in your complex number, so it's the real unit without the variable I. And then B is your imaginary unit that does have the I with it. So let's backtrack for just a quick second and remember how to graph a point. If A comes first, what variable is he acting like? X, you got it. So if he acts like the X variable, how does he move?
Left or right.
You got it, left or right. So if it's negative, we're going to move him left. And if he's positive, we're going to move him right. So that's the very first part we move on a coordinate plane. So if B then comes second, what's B acting like? Y, we got it, and Y moves us how? Up and down. So negative goes down, positive goes up. And we always do our Y value second. Alright, so for our examples, we start off with our first example being the square root of a -36. So our first example, EX for example, there we go, is the square root of a -36. And we're asked to write the square root of a -36 using imaginary units. So here's the thing we know. If I were to put in my calculator right now the square root of a -36, what would it tell me? You got a non-real calculation. It gives us that error message. So what part of it is giving us the trouble? The negative. So we're actually going to separate this guy out into a square root of a +36, which would mean I'm taking out a square root of a -1. And now we can do this part in our calculator. What is a square root of a 36? 6. All right. And the square root of -1. That would put it in our calculator, but what did we just say the square root of -1 was? So the square root of -1 is the same thing as what? So like remember, these two guys will be interchangeable. So instead of saying the square root of a -1, it's actually going to become our imaginary unit I. And now there's a nicer way to write this. How can I write 6 times I better? Just 6I. So go ahead and just write them side by side. And my board has a goofy spot right there. Do you all see that? It went up 3 times on me every time I try to fix it. Alright, so 2, exact same kind of scenario. We have the square root of a -625. So same bit as before. We're going to have to separate it out. So what do I separate it out into? You got square root of a +625 and the square root of a -1. And now we just reduce it. What is the square root of 625? 25. You got it. And what do we say the square root of I gave the answer. What does it say the square root of -1 became? And we're just go ahead and write them side by side. So example 3 wants us to graph it. So example 3 says, what is the graph? We're asked to graph our -5 plus 3i. So that goes back to complex numbers on a coordinate plane. So if you remember, our complex number is always going to be a plus bi. So what's our a value? -5. And our b value? 3. So now let's make an 80 coordinate plane. I just made mine 5 in every direction. So if you just want to make it x-axis with 5 tick marks in every direction, and then your y-axis and 5 tick marks in every direction. And then we're just going to plot the point. How do I graph the point -5, 3? Where do we go? You got left 5, then up 3. Whenever you make those points, it's actually correct if you label them. So -5 plus 3i. So we label it as a complex number. And we're good. First one's done. So our next graphing one, let's see if I can get rid of this screen here. There we go. Wants us to know, oh, it should just say just the graph. We don't have to do the absolute value. So what's the graph of each number? And so for example, 4, it says 6i. So this time, if we think about our complex numbers and writing our order pairs, what always comes first in the complex number? A plus bi, you got it. So if I go to write my a value, well, what is a? It's just going to be 0 because there's nothing there. So it'd be like 0 plus 6i. So a is just going to be 0, and then b is going to be what? 6. You got it. And for this one, if you want to, just make your x-axis just go left and right, maybe 2 or 3 parts. Then your y-axis has to go up to 6. So that one we can make a slightly smaller graph just because where does the 0 going to send me to start with? You got it right there at the origin, right smack dab in the middle of the graph. And then where's 6 going to send me? Up 6, you got it. So right there up at 6, you're just going to get 6i, and we're good. That's how we graph our complex numbers. So our last set of examples, switch gears on us one last time, and wants us to find the value of. So at number 5, we're asked to find the value of I to the 13th power. Now, we have to get it in a value we can understand. So this is where knowing what I squared is helps out. So what is our value of I squared? -1. Now, because this is a square, we want all of the exponents to be even. So we're going to make exponents even numbers. So if you look at it, my first one here starts off with I to the 13th power. So is 13 an even number? No. So ask yourself, what's a number just less than 13 that is even? 12. So we're going to say I to the 12th power times. How many i's would I have left over? 1. So this goes back to like your monomial rules, knowing that if I have I to the 12th times I to the 1st, that actually makes I to the 13th. So all we've done so far is just pull out that one extra I in order to make it an even exponent. Now here's where we go back to another monomial rule. So my I to the 12th, I'm going to write it as I squared and wrap it in parentheses. So I'm going to make I to the 12th become I squared. And now we have to remember, if I raise a monomial to a power, we're multiplying the powers. So we're actually doing the opposite. So we have to divide. What's 12 divided by 2? 6. And I drop down my times I. So I'm going to hang up here for just a second and just show you that we've not changed the numbers at all yet. All we've done is just kind of used our monomial rules from way back in Unit 2 to break it down. So I said I to the 13th became I to the 12th and I to the 1st because 12 and 1 is 13. Now, working backward with your monomial rules, we do 12 divided by 2 and get 6. So if you work forward, what's 2 times 6? 12. 12 plus the 1, 13. So it still all adds up to 13 as far as the exponents go. All we've done so far is just use monomial rules. Now, last little bit, this is the most important part, why it's red up here. I know I squared is what? Is that right for me? Negative 1. So I can replace this I squared here with negative 1. I'm going to get negative 1 to the 6th power times I. And now this is calculator work time. Put in your calculator parentheses and all. Parentheses, negative 1, parentheses to the 6th power. What do we get? Huh? 1. We get a positive 1. And now what has to stay with it? The I. So 1I, and we're good. That's our final answer. I to the 13th power reduces to just 1I. So example 6. We have a negative I to the 24th power. Alright, so first things first, what technically is in front of my I here? Negative 1. So I'm going to pretend it's like negative 1 times. Now, is my I to the 21st already even numbered? Yeah, so we're good. So we can actually go ahead and write I squared because he's already even. And now what did we say we did from here to here? Divide. So what's 24 divided by 2? 12. Alright, now we get negative 1 times, what do I know I squared is going to become? Negative 1 to the 12th power. And it goes back to calculator work time. So what's negative 1 to the 12th power? You got positive 1, so it's going to be negative 1 times negative 1 to the 12th power is positive 1. And now what's negative 1 times positive 1? Yep, you got negative 1. Negative 1 times 1 is negative 1. So while we have these up here, there's a couple of things I just kind of want to make note of. That way as you do examples later on, you'll be like, oh, that's what they look like. So if you have an odd exponent to start with, so odd exponent, you always end up with an odd answer. So if you start off with an odd exponent, I is in the answer. Whereas if you notice over here, where I start off with an even exponent, what do I not have? There you go. We don't have an I anymore, so no I in the answer. There's also a couple of other little things if you remember about your rules. If you're going to raise anything, alright, this will help out too. So if you raise negative 1 to any even power, it's going to equal a positive 1. And if you were to raise a negative 1 to any odd power, it would equal negative 1. And that goes back to just knowing, like I squared. That's an even exponent. Negative 1 times negative 1 is positive 1. But if you have an odd exponent, that would be negative 1 times negative 1 times negative 1. So it's always going to come out to be negative. So it's those little rules like that right there. And we're all good. That finishes this up.